Hello dear students, welcome to the channel and welcome to this playlist in which we are discussing about over voltages and transients in power system. So up until now in earlier videos we have discussed about the over voltages problem in the power system. We have discussed about what is over voltages, what is a surge, how it is caused, what can be reasons behind it. We have discussed about different type of surges and how different type of over voltages takes place in my power system. We have discussed in detail about lightning and how does it takes place, how does it form, how it can affect my power system, what are the harmful effects of lightning on my power system, and how can we uh, prevent the danger caused by lightning. We've also seen how we can defend our power system from lightning by using different equipments and taking different measures. We've studied about lightning arresters in detail. Lightning arrestor or surge arrestor, you can call it whatever you want. We have studied about them in detail. We have saw its types and we have saw different type of surge absorbers as well. Today we are going to talk about the transients in power system. By the way, it is a whole new chapter, so we are covering both of these chapters all together, and this will probably the last chapter of the coursework of power system 2 of GTU. So if you have made it till here this far, then congratulations. We are going to cover the last chapter as well. But now that we have reached the last chapter, I would like to tell you that power system is very weird and bizarre subject in its own, right? And how? Because 90% of the operation which takes place in the power system, during all that time my system will be under steady state condition. In fact, I would like to say that more than 99% of times my system would be under steady state conditions. But the 99% of problems caused in the power system would be by that 1% condition of transient. See, how bizarre is that? How weird is that? Only 1% of transient, like 1% time which is occupied by transients in power system, is responsible for more than 99% of problems caused in the power system, right? And how and why does this transient occurs, we are going to discuss about that in detail as well. So without wasting any time, without further ado, let's get started. By the way, we have discussed about the lightning arresters and different types of it, and we have discussed about surge absorber in detail as well, how surge absorber differs from lightning arrestor in detail as well in the previous video. So if you haven't checked out the previous video, click on the top right hand side corner of your screen in the I button, and you will be there you will be able to watch it. Now that out of the way, let's get started. We were about to discuss what is a transient and what are the causes of transient, right? So normally transients are produced in the system because of abnormal operations, and these various normal operation conditions, what these conditions can be. So it can be switching operation, it can be opening or closing of any switch, it can be the sudden change in the load, sudden increment or decrement. It can be anything, either increment or decrement, it can be anything. Or the most famous condition, the short circuit, sudden short circuit, right? By the way, what is short circuit? So you can also say, if you have seen the lecture series of ours in which we have discussed about symmetrical and unsymmetrical faults, the LG faults, line to ground faults or line to line fault, these are the short circuit faults, right? And what is the last and most rare most rare occurrence of abnormal operating condition? That would be lightning discharge. We studied in the couple of lectures ago as well. So these abnormal operations produces a large current and voltage in the system which are higher in magnitude compared to the steady state condition, and such current and voltages are known as the transient current and transient voltages. And this is not a big news for us that these transient voltages and currents damages the equipment in my power system, and hence it is very important to protect my equipments from these transient current and transient voltages. So for 3 to 4 lectures now on, we are going to discuss about the transient. We are going to study the transient produced in the simple circuit, alternators, and we are going to discuss about the concept of restriking voltage produced after removal of a short circuit. We are going to see concept of traveling waves, the attenuation of traveling waves, and the transient produced due to the capacitance switching, and topics like these. But first, I want to discuss about the review of the transient simple circuit. If you have taken this circuit and network courses, network topology, if you are familiar with this, you might already have some idea. But for those who are not familiar, I'm going to explain a simple RL circuit. So take a look at this circuit in the figure. We are taking an AC source. The voltage source is giving voltages Vm sine omega t plus alpha, and the load connected on the other side is RL load with a switch in between. Pretty simple circuit, right? Nothing big in here. Now, what will be the circuit equation? Can you tell me? Just apply the Kirchhoff's voltage law or KVL throughout the circuit and tell me. So the equation will look something like this. See, Ri plus L di by dt, which means the power consumed by load, will be equal to Vm sine omega t plus alpha. Right? Not power exactly, voltage. Right? So voltage consumed by the load will be equal to my supply voltage Vm sine omega t plus alpha. And again, no need to mention that where I is an instantaneous values of current, the alpha controls the instant of the voltage wave, and when in the closed switch condition. And if I want to solve this equation for the value of I, if I want to make I the subject, how can I write this equation? So if I want to make I subject, I have to take integration on both the sides. However, they have skipped one step and directly showed the equation, but I have to take the integration on these sides, and at the end I will reach to this equation. Right? So the final value will be I will be equal to Vm sine omega t plus alpha minus theta divided by under root of r square plus omega square plus L square. And even completing this formula, if we call this r square plus omega square plus L square equal to z square, or z, because it is in under root. So what we will get, we are simply taking the impedance cumulatively, right? So I will be Vm by z sine omega t plus alpha minus theta, right? And what is theta here? So theta is basically tan inverse omega L by r, right? So it is nothing but tan inverse of my omega L, which is um, which will be the frequency over here divided by r, right? And now when I apply the initial condition at this equation, if I call the voltage is equals to 0, then LDI by dt plus Ri will be equals to 0. And following this equation, what I will get based on this initial condition, I will get value of I equal to A into A e raised to RT divided by L. And we can find out the value of A by substituting the value of I here, right? So what we will do, we will simply put I equal to this term, the whole term, plus Here, by the way, here will be I0. This is for the initial condition, so this will be I0, not I only. So you have to write plus I0 here, and this will be I0. So you have to add this term over here. A e raised to minus RT divided by L. This whole term will be equal to 0. So what you will be left with will be this. The value of A will be minus Vm by Z sine alpha minus theta, and hence the solution of my final solution will be, this term was there from the beginning, right? Then we put the value of A minus Vm by Z sine alpha minus omega and e raised to minus RT divided by L, right? So we just substituted the value of A in this equation. Simple enough. Now in this equation, the last equation, the current I has two components. First one would be the steady state component, which stands for, of course, steady state current, or also known as sinusoidal component. It will be having amplitude Vm divided by Z, and it is lagging in the voltage lagging the voltage phasor by what angle? See here, theta angle. The second component would be the transient component, and this will be that little nasty component which will be causing trouble all the time. And that transient current is also known as a DC offset current. So what it will do, it will decay exponentially corresponding to the time constant L by R, because of this term, right? Decay because of minus L by R is given here, and exponentially because we are having exponential function here. And by the way, if you just want to be sure, you can see from the image here we are having the original component. This was my Vm by Z sine theta minus alpha. You can see the delay alpha here. Here is the theta. This is the current waveform. The bigger one is the current waveform. This is the voltage waveform. So you can see here that voltage is lagging the current by alpha angle, right? And you can also see the difference in the peaks of my current and voltage in the form of theta here. Now the DC offset, or the transient waveform, or transient component we talked about, can be seen here. This is my IT DC offset. It is decaying exponentially corresponding to time with respect to constant L by R, and it causes the total current to be unsymmetrical till the transient decays. So basically this is getting multiplied with this, and the output is this. It is getting multiplied with current because this is the current's formula, right? So output is this. See, it is exponentially decaying. Now if the switching takes place at an instant where alpha is equals to theta, the DC component will be 0 and the current wave will be symmetrical. So in case of alpha equals to theta, the current will be symmetrical. And if switch is closed when alpha minus theta equals to 90 degrees, or rather we can say plus or minus pi by 2, then the DC component will be maximum, and the first peak of the resultant current I will become twice the peak value of the final steady state current, which is known as doubling effect, by the way, which is very dangerous. So that was the basic review of transient for a simple RL circuit. Now I want to discuss about the short circuit and alternator. So it is very famous that during any abnormal conditions, abnormal operations, the alternator can be subject to transient conditions. And these short circuit may develop severe mechanical stress on my armature coil. Remember, we have armature in the alternator. This will develop large torque which may damage my alternator, or even bad than that, it can damage its prime mover, the prime mover of my alternator. And because of that, it is very important to protect my alternator. And how we can do that? We can do some analysis. We can do analysis of my alternator under transient condition in order to predict the possible condition that can result in the abnormal operations. So during the short circuit analysis, the armature and the field winding of the alternator is assumed to be purely inductive. And being a student of sixth semester, you may aware of it. You have studied machines in the fourth semester, so I think you all are pretty much aware of it. So we all know that we assume that alternator is purely inductive and it does not contain any capacitance and resistances. Even if they contain something, then the value of that capacitance and resistance will be very negligible. And because of this fact, the flux linkage in the armature or field circuit cannot be changed suddenly by applying short circuit to armature winding, right? We cannot change the flux linkage in the armature coil by just applying short circuit current. So the current flowing through armature of my alternator when its terminals are short circuited will be similar to that the current flowing in the RL circuit, what we just saw. But in RL circuit, reactance is constant, right? It is constant. But in alternator, the reactance is a function of time, remember? So let's say alternator is operating at a no load condition, and under normal operating conditions there is no mmf because of armature reaction. So when three phase short circuit occurs at my terminal, the current in the armature will increase to very large value, right? And as resistance of my winding is very negligible compared to the reactance. Also again, if you have studied about the alternator and uh, alternator and armature reactance, then you might have idea about this, right? The resistance of winding is very negligible compared to the reactance is very high. So the current is highly lagging and the power factor is approximately 0. Now this sudden increase in the armature current will produce armature reaction. The air gap flux will not be able to change instantaneously and the armature reaction will oppose the main excitation. Now, in order to counter this demagnetization current, uh, we will have, in order to counter this whole situation, the demagnetization current will appear in the field winding and damper winding as well, which will help the uh, main flux. So now in the initial part of the short circuit, the equivalent circuit of alternator will appear, as you can see in the very first image here. Under steady state condition, the armature reactance of alternator will produce demagnetizing flux, and we can represent it using XA. The short circuit current decay in accordance with the winding time constants, and the time constant of the damper winding will be much less than the field winding. Now, damper winding has low leakage inductance and field winding has a high leakage inductance. Always remember that: damper winding, low leakage inductance; field winding, high leakage inductance. So in initial part of short circuit, the damper winding and field winding have transformer currents induced in them, and because of that, the circuit will model the reactance XF XD omega will appear in the parallel with XA, which you can see in this image: XD XF XA, right? Instead of X d omega, you can write XF as well. Basically it is frequency. So as a damper winding, As damper winding currents are first to die out, the X d omega effectively become open circuited. Now this d omega will become open circuited, then we are having just two of these, XF and XA, in parallel, as you can see here, right? So once it dies out, uh, XF will become open circuited. The machine reactance changes from parallel combination of XA, XF and XD omega, which was during initial period of short circuit, to XAXF in parallel, which is the middle period of short circuit, and later on to XA in steady state. By the way, this state is known as subtransient state, this is known as transient state, and this is known as steady state. The reactance of machine in the initial period of the short circuit is called subtransient reactance, because it is reactance of subtransient state, and it is expressed as xd double dash, which is basically you can calculate it from this equation here. We are having the value of xf plus 1 by, because all three of them are in parallel, d x d omega plus xf plus xa. Simple. Then for the reactance effective after damper winding current is dies out, it is called transient reactance. Basically it is because showing the transient it is effective in the transient time period, and it is expressed in xd dash. And you can see the formula of xd dash. You can form the formula of xd dash from this equation. You are having xf in parallel with xf and xa, which means xf plus xa into xf divided by xa plus xf. Pretty simple. And final is basically sum of xf plus xa for steady state, which is known as steady state transient reactance, which is basically a synchronous reactance of my machine as well, right? And obviously the value of the this reactance will be far greater than the value of this sorry the value of this reactance will be far greater than the value of this, and value of this one will be far greater than the previous one, which means xd double dash will be the smallest and xd will be the highest value of reactance. And that is why I was saying that in alternator the machine offers a time varying reactance based on the value, or based on uh, if it is in transient state, steady state, or in subtransient state. Now as we were discussing, let's analyze this short circuit current first. So when short circuit occurs at the terminal of synchronous generator, the initial short circuit current is limited by the subtransient reactance. The short circuit current will consist of symmetrical components and DC components. As we discussed earlier, it will have symmetrical component and DC component. Now, the voltage of three phase are 120-degree apart, we all know, and the short circuit will occur at different points on voltage of each phase. So the DC component will be different in each phase. Now, if DC component is negligible enough, the oscillogram of armature current will look something like this, as you can see in this image. As you can see, initially the current is limited by subtransient reactance. After few cycles, it is controlled by transient reactance, and finally it gets settled down by steady state value to the steady state value, which would be limited by synchronous reactance of my machine. Right. So basically, we can divide the short circuit period in three periods: subtransient period, as you can see, for very small amount of time; transient period, which would be a little bit longer than subtransient period; and then steady state period, which is almost eternal. In subtransient period, the value of current would be too high. In the transient it would be still high but decreasing, and in steady state we will be having continuous value of my current. And we have indicated it with with these indications: I double dash max c, I double dash max b, and I max a. Now let's discuss about the sub-transient period a little bit. So it lasts only for first few number of cycles during the current decrement is very rapid, and after this the transient period will cover relatively large amount of time during which the current is continuously decaying in moderate manner, and finally then steady state period will arrive. So based on that, I will be OA divided by root 2, which would basically equal to E divided by XD for steady state conditions. For transient condition, it would be OB divided by root 2. Basically, you can see here A, B, and C. So this is for transient, this is for steady state, and this is for sub-transient. Sorry, this is for steady state, this is for transient, and this is for sub-transient. So OA divided by root 2 would be I for steady state would be equal to E divided by XD. Basically, E is the RMS value of my phase voltage and XD is the direct axis synchronous reactance. I dash, and by the way, I is the RMS value of the steady state short circuit current in case you're wondering. Then I dash would be the RMS value of transient current, which would be equal to OB divided by root 2, which will mean E divided by XD dash. XD dash is the direct axis of transient reactance. Earlier we saw for synchronous reactance. And then finally for I double dash, which would be basically the RMS value of subtransient current, can be given by OC divided by root 2, as you can see here, OC divided by root 2, which is basically E divided by XD double dash, and XD double dash is the direct axis subtransient reactance. Now let's see the restriking voltage after we remove the short circuit. What happens then? So when the circuit is basically open under fault condition, it produces transient known as the recovery voltage transient. And this transient will affect the behaviors of the circuit, interrupting and protecting devices, which you can see in this image. Right? It is showing the simple circuit in which a load is fed through a circuit breaker. As you can see here, it has been fed through a circuit breaker, which is occurring at a fault and in occurrence of the fault, suddenly it will isolate the load. Now during this time the heavy fault current will flow through the circuit, which is limited by the inductance, and C is the natural capacitance of the circuit adjacent to the to that circuit breaker, as you can see here. The circuit breaker contacts are opened to clear the fault, and this it is self itself will not interrupt the current, as the arc will be produced between the contacts. So current will continue to flow through the arc, but the successful interruption of the current will depend on controlling and finally extinguishing the complete arc itself, and that interruption is affected at the instant when current will become zero. So for the analysis of circuit, the time is measured from instant of fault interruption. And how do we do it? So by using this formula, you already know the equation. You do know how do you form the equation for this circuit, right? It is basically LC circuit, so it will be L di by dt plus VC, the voltage across capacitor, will be equal to my voltage source Vm cos omega t. Right, I don't need to mention what is I and what is VC, right? Now how do you relate I and VC? So we all know the current across the capacitor is given by C dv by dt. So that way both of them are relatable. So instead of that Vm cos omega t, can't we write this thing, right? First, d square Vc by dt square plus Vc divided by Lc, we can compare it, right? You know the value of Vc. based on this formula. So you can put it over here, right? So finally you will get d square vc divided by dt square plus vc by lc equal to vm divided by lc cos omega t, right? So basically what we are doing, we are dividing the whole term by lc, and also clearing the current from here, right? Basically substituting value of current over here. So now I want to move from this frequency domain to time domain. I want to change the domain. So what do? We can take the Laplace transform of this equation, and we can substitute the omega 0 square for 1 by LC, and by doing that we will get equation which will look like this: p square vc of s minus s vc 0 minus v dash c 0 plus omega 0 square vc of s will be equal to omega 0 square vm plus s divided by s square plus omega square. And here you already know vc of s is the Laplace transform of vc of 0 is the value of vc at z time equal to 0, and v dash c 0 is the value of dvc by dt at time equals to 0. Now when we neglect the arc voltage vc0, the equation will look something like this: vc dash 0 will be equal to I of 0 divided by c, which will basically equal to 0. Now that we have settled value of vc and vc dash equals to 0, the equation will look something like this, because we have settled the value of vc dash and vc equal to 0. So vc dash of s will be equal to omega 0 square vm s divided by s square plus omega square plus s square plus omega 0 square, and you can represent it using this formula as well in a little bit different manner. Nothing new here, right? Because basically it will become s square plus omega square whole square, and when you have a square of that, you can represent it in this way as well, differently. Simple. Now you want to find the inverse of it, so you have to find the inverse Laplace. So you have to take the inverse from this equation, and vc will be omega 0 square vm divided by omega 0 square minus omega square into cos omega t minus cos omega 0 t, because basically this is the Laplace transform of cos omega t and cos omega 0 t, right? If you are not aware of Laplace, please check out the playlist in which we have discussed about the Laplace transform. uh, we have discussed about Fourier transform, Laplace transform, Z transform in detail, so you can check out the video. The link will be in the description, or if possible I will provide the link in the I button as well on the top right hand side corner of your screen. So please check it out if you are not aware of it. Now once we find out the value of vc, there is one thing we generally take care of is the value of omega 0 will be way more than value of omega. Why? Just so that the uh, ratio of omega 0 square divided by omega 0 square minus omega square comes to as close as possible to 1, so that the value of vc will be equal to vm cos omega m minus cos omega 0 t. Remember we studied it earlier when we started the chapter. So the natural frequency oscillations will persist a small interval, and during this interval the change in the power frequency will be very small and it will be very negligible. And if we neglect that, then this cos omega t will be removed from this equation. So ultimately we will have vc equal to vm into 1 minus cos omega 0 t. And to understand that, see this figure. It shows the transient recovery voltage across my circuit breaker, which is given by vc here, and you can also see where the fault has occurred and what is the actual system voltage here, right? So once we remove the fault, the source will change. The source charges the capacitance, and the interior of circuit inductance causes an over switching of my voltage. So the system losses will damp the oscillations provided during this period, and the voltage Vc will be transient recovery voltage. If nature of frequency omega 0 is high, then the voltage across the circuit breaker contacts will rise quickly to the higher magnitude. And if this rate of rise of recovery voltage will exceed the rate of rise of buildup of electrical strength of the space between contacts, the arc will restrike. And this restriking of arc will delay the circuit interruption for further half cycle. And because of the possibility of the restriking of an arc, the transient recovery voltage is also known as restriking voltage. So that was the restriking voltage. And now, when we discuss further, we are going to discuss about the arcing grounds. But I think today's video, we will keep today's class till here. Whenever we meet next time, we will be discussing arcing grounds. So if you have any doubts, any queries, please feel free to mention them in the comment section below. I will try to answer them as many as possible, as soon as possible. And if you have any feedback for the channel or this playlist, everything is welcome. Please mention them in the comment section below as well. So I will be seeing you next time with the arcing ground. Till then, take care of yourselves. Thank you very much and goodbye for thank you very much for listening and goodbye for now.